勘が良さそうだから。
Okay, just letting everyone into the Zoom room. I'm happy you all found the link. Is there anyone else in the waiting room? So today is the third last lecture of the semester. I hope I've announced on Blackboard the date of the final exam, which is, I believe, if I remember correctly, it's May 24th at 10:30 a.m. It will be 2 hours and 15 minutes long. That is the allotted time as dictated by the college. Homework number 5 is due on Wednesday midnight. It's a good opportunity to practice first and second order circuits. And today the plan is to do the second half of lecture number 9, where we are delving into analysis of AC circuits and specifically how to represent circuit elements as phasors.
Sir.
Yes.
When are you gonna upload the slides number 8 so?
Oh, yeah, it's a little bit different for lecture 8. Let me just do it right now, just so I don't forget. For lecture 8, I upload all the all of my solutions to the practice problems, and I have a scanned PDF with all of the solutions. But it's a good question because okay, so they're up now. I just want to make sure that yeah, this is everything. Okay, they're up there now. Thank you for the reminder. Oh, I'm sharing my screen. Okay. So today, what we're gonna do. Oh, one more person that I have to admit. 2 more people. So today, what we're going to cover is how to it's a form of Ohm's law for capacitors and inductors. So For resistors, we already know that V is equal to I times R. And today we're going to extend that notion to be V is equal to I times Z, where Z models something known as impedance. And unlike resistance, which is only, is only true for resistors, impedance applies to resistors, capacitors, and inductors. It's like a complex version of impedance. Yeah, I know. I haven't started yet. I'm about to. I'm just giving you the overview. Okay. So right. So we from last class, what we covered. What we covered is just how to represent a voltage or a current as a phasor. And so basically, a phasor is just a vector or a line with an arrowhead, whose length is the amplitude of that sinusoid, and the angle with the x-axis is the phase. And so that represents a sinusoidal signal, and that can be a voltage or a current. So now what we're going to do is cover how to actually analyze circuits that have sinusoidal voltages, sinusoidal batteries, and sinusoidal current sources. And those circuits can have resistors, inductors, or capacitors. And you'll see here that when you go to complex numbers for everything, it just makes your life a lot easier because when we work in the phasor domain, we just basically can use Ohm's law for everything. Okay, so let's start with the resistor. We know that V is equal to IR, and that holds for all time. So let's assume that the current I is a sinusoid with an amplitude of I sub m and a phase angle of phi. Okay, so this is our current source, has an amplitude and a phase angle. And we've agreed upon a frequency, like in North America, maybe 60 hertz, which would be 120 pi in radians. And that gets put across, that current flows through a resistor R. And then we know that the voltage is just going to be equal to the current, but with the magnitude scaled by R, right? So in other words, the only difference between the voltage and the current is that there's this extra R, which is a real number that's multiplying the amplitude of that sinusoid. So in other words, the phasor V is equal to the phasor I times R. What this really means is that for a resistor, the phase angle doesn't change. Right? So the phase angle of the current is the same as the phase angle of the voltage. That's only true for resistors. That's not going to be true for capacitors and inductors, as you'll see in the next slide. So if you're wondering why we even need this equation, well, we need this equation because it shows that the magnitude of the voltage scales the resistance, but the phase angle stays the same. So a picture of this would be, this picture here is a time domain, and this picture here is in the phasor domain. It's depicting the same thing, but here I is a constant, like a DC constant, and boldface I here is representing a sinusoid. And so the voltage across this resistor, which is a phasor V, is equal to the phasor I scaled by R. And the picture, I think this is the most illustrative way of teaching this. If you have your current I, then the voltage phasor is pointing in the same direction as I. In other words, it has the same phase angle, but its length is scaled by the value of R. So in this case, the value of R is like 2, right? It looks like the voltage phasor is about twice the length of the current phasor. So this would model the case of a resistance of 2 ohms. Okay, I think that's all pretty clear. Now, the interesting case is when we move to inductors. right? So let's say you have a current I that's flowing through an inductor. And what we saw well, let's actually go through it. Let's actually derive from scratch. We know that the voltage across an inductor is proportional to the derivative of the current. And so let's assume that the current is a cosine with a phase angle of phi and an amplitude of I sub m. Let's differentiate that with respect to time and multiply it by L. And so when you take the derivative of a cos, it's equal to a negative sine. And the omega gets put through because of the chain rule, because it's omega t, not t. And so now we want to know what this looks like in the phasor domain. So we need to do two things. One, we need to transform the sine to a cosine, because we've agreed that our phasors are going to represent cosines. And we need to, what's the other thing that we need to do? Right, and we need to account for, right, we need to move the sine to a cosine. When you do that, the nice thing is that the negative sign drops out, but you get this extra phase shift. Right, so the magnitude of the cosine, of the voltage cosine, is omega times L times Im. But now the phase angle has a 90-degree head start. In other words, the voltage is 90 degrees ahead of the current. Right? So in other words, if you pass a sinusoidal current through an inductor, the voltage that's generated across that inductor has a 90-degree offset relative to the current. And so these three steps, basically what we're doing here is just transforming this into a phasor. So what I'm marking here with my cursor, that's the magnitude of the phasor. And the phase angle is phi plus 90. And at a phasor, so this phasor is just equal to J. Right? So it has a magnitude of 1 and a phase angle of 90. Right? So if the horizontal axis is the real axis, and if the imaginary axis is the imaginary, then EJ90 is just equal to J, or 1J, or 0 plus 1J. And so the voltage phasor is equal to, denoted by capital boldface V, is equal to J omega L times I. And so this is really convenient, because if we know what our current is, we can just, and our current is now a complex number, we know what the voltage is simply by multiplying the current by J omega L. So I is a complex number, J omega L is a complex number, and V is a complex number. And so so now we notice that this is basically a form of Ohm's law, where J omega L is basically the impedance. And so we see that the voltage is 90 degrees ahead of the current. And as a picture, this is the kind of the classic picture for an inductor. You have your current phasor and you have your voltage phasor. And these are rotating around this plane. And the rotation around this plane is equivalent to the fluctuating sinusoid. And so at any one time instant, the voltage phasor is going to be 90 degrees ahead of the current phasor. And this is the mathematical expression of that fact. So the other nice thing is that for a capacitor, you basically have the same result, but in reverse. So again, we know that the current is equal to C times the derivative of V. And so if you do the exact same steps as before, what you see is the current I is equal to J omega C times V. So if we want to have the voltage expression, we just divide through by j omega c, and you get the voltage is equal to I over j omega c. In other words, the voltage is 90 degrees behind the current in this case. So it's the opposite direction. So if you have a current that you're passing through a capacitor, the corresponding voltage is 90 degrees behind at all times. And the length of the phasor just depends on the value of omega c, basically, because the magnitude of j omega c is just equal to omega c because it has no real component. And so this table here is very useful. You should basically have it kind of stored in your long-term memory, at least until May 25th. So you have voltage is equal to R times the current for a resistor. For the inductor, you have that voltage is equal to j omega L times I. And for a capacitor, you have that V is equal to I over j omega C. Okay, so what these are telling you is that if you pass a current through an inductor, this is the voltage that envelops across the inductor. If you pass a current through a capacitor, this is the voltage that envelops. And then in all cases, the frequency of the voltage phasor is always, the frequency of the voltage sinusoid is always the same, but its amplitude is scaled either by j omega L or 1 over j omega C. And it's always either 90 degrees ahead of the current or 90 degrees behind the current. So this is like, it's a very well-known result in basic AC circuits, that for a capacitor and an inductor, the voltage and the current are related to each other by 90 degrees. And this is just follows from the fact that the derivative of a cosine is a sine, and the derivative of a sine is a cosine. Okay. Let me just one second. Okay. If there's any questions about this, please feel free to jump in. We're going to do some basic examples to kind of get your feet wet on how to use these new ideas. Our first example, we're given that a voltage is applied to an inductor. That voltage has an amplitude of 12, a phase angle of 45 degrees, and a frequency of 60. The inductance is 0.1, and we are asked to find the current that's flowing through the inductor. So the first thing that we want to do is just figure out which equation we want to use. So this is the equation that relates the voltage to the current across an inductor. Okay, so let's represent our voltage. We know the voltage is equal to 12 angle 45. Why? Because it's already expressed as a cosine, which is what we need. The amplitude of the sinusoid is 12, and its phase angle is 45. And so now basically we need to take this number and we need to divide it by j omega L. So what is j omega L? Well, here is going to be j times 60 times 0.1. Because this here, this is the omega, and this is the L. And so j times 60 times 0.1 is equal to 6j. So probably at least one of you is wondering, why is it? So if you have your imaginary axis and your real axis, why is it that if you have 6j, right? If the value of this line, the length of this line is 6, right? This is the J-axis. Oops, I drew that the wrong way. I wanted to draw it this way, right? So this is our phasor, and the length of this phasor is 6. Why is it that this phasor here, that I'm trying to make, the blue phasor here, why is it equal to 6 angle 90? Why? Because its length is 6 and it has a 90-degree angle. And so 6J, this is equal to J times 6, is equal to 6 angle 90. And the reason we convert this to this is so that we can carry out the division of these two phasors. So 12 divided by 6 is 2, and 45 minus 90 is minus 45. And so given that the current phasor I is equal to 2 angle negative 45, what is the corresponding, ask you guys, what is the value of I of t as a cosine? So if I want to express that phasor as an actual, yeah.
Would it be 2 cosine 60t minus 45?
Excellent, yes. Exactly what it is. Sorry. 2 cosine 60t minus 45. Let me just clear my annotations. Okay. Yeah. Very good. All right. I think we have one more example just like this. Okay, yeah. So this time we're dealing with a capacitor. We're given that a voltage of 6 times cos 100t minus 30 is applied to a 50 microfarad capacitor. And we are asked to evaluate the current through that capacitor. So we know that the current for a capacitor is equal to j omega c times V, where I and V are both phasors. So the first thing we need to do is express the voltage as a phasor. Right? So who can help me with expressing this sinusoid as a phasor?
Six angle negative 30.
Yeah, 6 angle negative 30. And then what is going to be the value of j omega c?
J 5000.
Yeah, that sounds right. It's j times 100. I think is it 5,000 or 50? Yeah, it's j times 100 times 50 times 10 to the minus 6. And so right. And so this, yeah, that's right. J 5,000 times 10 to the minus 6. And so this here that I'm highlighting is just the j omega c, and that gets multiplied by the V. And the V is equal to 6 angle negative 30. And so let's combine all the coefficients. That gives us 30 times 10 to the minus 3. And the J is still here. And so the J can sometimes cause confusion, but just remember that J always is just equal to 1. And I don't know how to draw the angle. I'm just going to draw it like that. J is equal to 1 angle 90. Right? And so in this case, all you have to do is add 90 degrees to this angle without changing the magnitude. So it becomes 30 times 10 to the minus 3 angle 60, which means that the value of the current is equal to 30 cos 100t plus 60 milliamps. Okay, is there any questions on the last two examples?
In order for us to write it in the cosine form, we need to know what omega is to begin with. Like we can't just get it in a phasor form.
That's a good question. So if you get, we'll never ask you, if you just get the phasor, we'll either tell you what the omega is, or we're not going to ask you to convert back to a cosine. But yeah, that's exactly right. You need to know what the omega is, because the phasor is really one per every frequency. So the frequency changes, it's an all new phasor. And so this really brings about this whole idea of, if you have, if you have a time domain, any time domain function, right, where this is time, that function can be represented in the frequency domain. And so, for example, this looks very periodic. So it may be something like, it may be something like that, for example. So these are two equivalent representations of signals. And I'm bringing this up because this is something that's common to all of engineering, like Laplace transform, Fourier transform, wavelet transform. There's so many transforms in engineering, and it's all about whichever representation is most convenient to work with. But yeah, if the phasor by itself, you don't know what the frequency is. All right, this next section is very easy. Basically, it's just kind of, it's a form of Ohm's law that applies to phasors. So we know that we have the relationship between the voltage and the current for all three circuit elements. And we can basically solve for the ratio of the voltage and the current for all three of them. And then we can call the resulting number here the impedance, because that is, the definition of, if you get, if you apply a voltage and then you measure a current, the ratio of those two things means something. It really is. That's why we call it impedance. It's how much is that element impeding the current that's flowing through it, right? And we're going to give this, we're going to call the units of this ratio to have units of ohms. Importantly, this is frequency dependent. And so if you apply a 60 hertz sinusoid, and then you measure the current, now if you change the frequency from 60 to 120, you'll get a different value of Z. If you measure the current and you divide V by I. And that's important. The big difference between resistance and impedance is that resistance is static. It doesn't change with frequency. Whereas impedance is generally frequency dependent. And so it varies with omega, for example. So the bigger the omega, the bigger the impedance of the inductor. The bigger the omega, the smaller the impedance of the capacitor. And we'll see what that actually means in the extreme cases in just a minute. Okay, so let's take the three cases, and let's apply the case when omega is equal to 0. So when omega is equal to 0, the impedance of an inductor is 0. So what does that mean? Impedance of 0 means short circuit. And that makes sense because the inductor at DC is just like a wire. So it's just passing that current through without any voltage drop. On the other hand, for a capacitor, let's take omega is equal to 0. Anything divided by 0, unless it's 0 itself, is infinite. And so the impedance of the capacitor for a DC source is infinite, which means that the capacitor is an open circuit at DC. So again, I'm going to just draw a picture of what it exactly. So if you have the time axis, this is time. The term DC always confused me when I was in school, but if you have, and if this is here, this is the called as the voltage axis. If you have a signal that is constant across all time, that's DC, right? And this is a DC voltage. It just means that it doesn't change with time. It's kind of I don't like the term direct current. I feel like it's a it's not a very like it's not the most clear term, right? It really means it really means time and varying. And so this, just go back. So that constant waveform is just modeled by a frequency of 0, i.e. it never repeats. So a constant value, a function whose value is constant never repeats. So its frequency is 0. If that makes sense. So the important thing is here for an inductor, at DC, it has no impedance. Whereas a capacitor at DC, it has an infinite impedance. And so short circuit, open circuit. The very interesting case is when you go to a very high frequency. So let's take omega to be a very, very large number. Let's take the limiting case when it goes to infinity. In that case, the inductor actually becomes an open circuit and the capacitor becomes a short circuit, which is interesting, right? So an inductor is a short circuit at 0 hertz, and it's an open circuit at infinity hertz, right? So if you try to pass a really fast signal through an inductor, you're not going to get any voltage at the output. You're going to get a 0 voltage. On the other hand, if you try to pass a very slow signal through a capacitor, you're not going to get much voltage. But if you try to pass a very fast current, you'll get a very large voltage because the derivative of a very fast signal is very high. So I feel like this infinity case is pretty interesting. And so Z is a complex number. And so it has a real part and an imaginary part. Okay? And we call the real part to be resistance, and we call the imaginary part the reactance. And so the reactance X can be negative. The resistance R is always positive, but the reactance can be negative, and it's generally negative for capacitors. And so the impedance is the sum of a real part and an imaginary part. Basically, the real part comes from a resistor, and the imaginary part comes from capacitors and inductors. And we can, because it's a complex number, we can express the impedance in polar form. We can also, if you want, express it in as a complex exponential, but it's most common to use this form, the polar form. So we can go back and forth between Cartesian coordinates and polar coordinates. And you guys hopefully are all familiar with the transformations between the two. Now this slide, this is not the most important thing, but we present it just to be thorough. Just like we talked early in the course about the inverse of the resistance being the conductivity. Oh, sorry. The inverse of resistance, what do we call it? Do we call it I think we call it conductance, not conductivity. So there's a similar concept for impedance. So the inverse of the impedance is known as admittance. And so the interesting thing is that now we're not taking the inverse of a number, we're taking the inverse of a complex number, which has, so it's basically 1 over a real plus imaginary part. And so for a resistor, it just is the inverse of the resistance. But now for an inductor, it will just be 1 over j omega L, which can be written as negative j over omega L. Now for a capacitance, the admittance is equal to j omega C, because again, the admittance Y is just the inverse of Z. And so if you take the inverse of, if you have a complex number and you take its inverse, so if you multiply the top and the bottom of this fraction by the conjugate of the denominator, so the conjugate of the denominator is r minus jx. And so what happens is, the reason that you do this is that you get rid of the imaginary part at the bottom. And all you have, the denominator is a real number. And so you have r over r squared plus x squared as the real part. And you have negative x over r squared plus x squared as the imaginary part. And so we just present this to show that the conductance, or sorry, the admittance is not necessarily equal to 1 over r unless you have unless the imaginary part x is equal to 0, right? So just be careful if you ever have, for whatever reason, it seems unlikely, you know, on the final, but if you ever have to take your impedance and take its reciprocal, excuse me, if you ever need to take the reciprocal of a complex number, you can use this trick for getting the imaginary part out of the denominator. Okay, so we're going to skip the example. We're just going to do this one. So this is our first AC circuit. We have a battery, which is expressed to us as 5 times sine 10t. And that battery is connected in series with a resistor and an inductor. And we are asked to find the voltage across the inductor and the current that's flowing through this circuit. And so one key thing is that whenever you're asked to find V of t or I of t, it means to represent your answers in sinusoidal form. And you can express it as a cosine or a sine. It's really up to you. However, to solve for the V and the I as a sinusoid, you will need to transform everything into the phasor domain. So for example, 5 sine 10t. Okay, so let me back up. We're going to solve for the current first. So we know that from Ohm's law, that the current, when expressed as a phasor, is going to equal to the voltage divided by the impedance of the circuit. So the impedance of the circuit is the sum of this resistor plus this inductor. Let me see if I can, I'm just going to try to annotate. So this Z is equal to 4. And this Z is called as ZL is equal to J omega L, which in this case is equal to, so our omega here is equal to 10. So it's equal to J times 10 times 0.2, which is equal to J times 2. So what's the value here of Z? If the impedance of the resistor Z is Z equals 4, and the impedance of the inductor is J2, what is the value of Z of the circuit total? So they are in series, so we can just add the impedances. So
4 plus 2J.
exactly, 4 plus 2J. So, right, so the impedance again is a complex number, and it's complex whenever you have inductors and capacitors. So 4 plus 2J. And now what is the value of the battery V expressed as a phasor? Remember that we need to represent it as a cosine before extracting its amplitude and phase shift. So as a cosine, 5 sine 10 of t is equal to 5 cos 10t minus 90. And so this becomes the magnitude, and this becomes the phase. And so what we need to do is divide this number by this number. I think that's gonna, right? So again, to convert a sine to a cosine, just remember just a 90-degree phase shift. So now you have, this is in polar form, but this is in Cartesian. So what I do first is I convert 4 plus 2J into a polar form number. So this is the polar expression for 4 plus J2. And then I can just divide the magnitudes and subtract the phase angles. And so my current expressed as a cosine is equal to 1.12 cos 10t minus 116.56. And if I want to go all the way back and express it as a sine function, I just add 90 degrees to the phase. And that becomes my current. Notice we are also asked to find V, which is the voltage across the inductor. So remember, Ohm's law holds. And so for an inductor, just call it VL, is going to be equal to I times ZL. Right, so I here, it's 1.12 angle negative 116.5 and our ZL here is equal to J times 2. Okay. And so we just plug in those two numbers. And for multiplying, so we need to multiply the phasor for the current, which is equal to this, by the complex number for the impedance, which is equal to J times 10 times 0.2, which is J times 2, which is 2 angle 90. So for multiplying complex numbers, it's easiest in polar form. And so this becomes 2.24 angle negative 26.6. And that can be represented as a cosine or as a sine by adding 90 degrees to the phase angle. Okay. Is there any questions about that example? Okay, I will take your silence as unconditional and total understanding. Let me move on. This stuff is easy too. Lecture 9 is a nice come down after lecture 7 and 8. Kirchhoff's laws. So Kirchhoff's laws apply always. It's like thing I always harp on. You can always apply Kirchhoff's laws because it's energy conservation and charge conservation. So they apply in the phasor domain. I'm not going to spend the proof is kind of unnecessary. So we know that around the loop, if you're going around the closed loop, the sum of the voltage drops has to equal to 0. So now let's replace each of these with a cosine function. And you have a bunch of cosines. And so the sum of these cosines, because those are the voltage drops at any given point in time across, across a bunch of circuit elements connected in series, we can represent those as phasors. And so this is a proof. I always say to students, it's good that you read through the proof. If you don't understand something, it's not the end of the world. Basically, the only thing that's tricky here is, it's not really tricky, but it's kind of, you may be wondering why we're doing it. So a cosine can be represented as the real part of a complex exponential, right? So what's inside the parentheses here is the magnitude, and what's inside the parentheses here is the magnitude and phase of this cosine. And what we notice is that this ej omega t term is a common factor to all these terms. And so we have the real part of everything that's in the parentheses times this complex exponential must be equal to 0. However, we know that the complex exponential function never is equal to 0. And why is that? Well, I guess the easiest way to explain why this function never can be 0 is if you look at a sine and a cosine on top of one another, they're never both equal to 0. Whenever one of them is 0, the other is at its peak or trough. And whenever the other is 0, the other is at its peak or trough. And so the complex exponential, the complex sinusoid, is never equal to 0, which means that what's in the parentheses here must be equal to 0. But what's in the parentheses here is basically the sum of phasors. So in other words, the sum of phasors around a loop has to equal to 0. All of that is to say that KVL holds for phasors. And similarly, you can show the same thing for KCL. In other words, if you have a whole bunch of sinusoids entering a junction, entering a branch, then the sum of those sinusoids at every given point in time has to equal to 0. And that means that the sum of phasors has to equal to 0. So if you have a bunch of vectors that add up to 0, it just means that like the geometric sum of those vectors ends up to be the origin, just a single point on the origin. So, all you really have to remember here is that KVL and KCL apply to the phasor domain equally. And so what this means now is that we're going to be able to apply all the techniques that we derived from KVL and KCL and apply them to AC. So things like nodal analysis, mesh analysis, we're going to be able to use those same techniques for phasors for in AC. And so, for example, let's take the combination of impedances. So let's say you have a battery, and this is an AC battery. So it's pumping out a sinusoidal voltage. And you're interested in understanding how much current is flowing through the circuit. and you have a whole bunch of impedances in series. So notice these may be resistors, these may be capacitors, or these may be inductors, right? They can all be represented by this complex impedance. And basically, we know that KVL holds, which means that this voltage rise V has to equal the sum of voltage drops V sub I. Right? So V, which is the battery voltage, which is a phasor, has to be equal to the sum of phasors around the loop. And so now let's write each of these sub-voltages in terms of Ohm's law. And because this is a series circuit, the current I is a common factor. And so then if you divide V by I, you get that the equivalent impedance is equal to the sum of the Z's. So, there's no surprise there. The total impedance of a series circuit, move this out of the way. So the total impedance of a series circuit is just the sum of the individual impedances. And so, for example, let's take a look at a voltage divider. Right here, we're gonna derive the voltage division principle in AC circuits. So let's take two impedances in series. We have a battery and we have a current. We know that the current, the total current flowing through the circuit, is equal to V over Z1 plus Z2. But we also know that V1 is equal to Z1 times I, and V2 is equal to Z2 times I because of Ohm's law. So if you combine Ohm's law with this expression, then you get that the voltage drop 1 is equal to the battery voltage multiplied by this fraction of phasors. So Z1 over Z1 plus Z2 times V is the voltage drop across the first load, and Z2 over Z1 plus Z2 times V is the voltage drop across the second load. So you use voltage division and current division in the exact same way that you did for DC circuits, except that now you just have to make sure that you know how to handle complex numbers, because the denominator is a sum of complex numbers and the numerator is a complex number. Okay. You can get the exact same result for a parallel circuit. So if you have a current source that is split into n impedances in parallel to each other, and so this, you have your current source in parallel with n impedances, you know that the current I has to equal to the sum of the individual I's here. So we know the big I, the one that's entering the first split, has to equal to the sum of this I sub I's. And basically, because I'm just going to flip back and forth, basically this voltage V, the voltage V is the voltage all along this node, is common to all of these loads. And so this I is equal to V over Z1. This I is equal to V over Z2, and so forth. And so we can represent I1 by V over Z1. We can represent I2 by V over Z2. And then it's easy to show that the equivalent impedance is equal to the inverse of the sum of inverses. So just like with resistors. And so, for example, if you have just two impedances, then their equivalent impedance is equal to the product divided by the sum, just like we saw in DC analysis. And we will use this in a few of the examples, I believe, in the last part of this lecture. And so again, there's nothing new here. You're applying current division and voltage division, but now you're doing it with complex values for the impedances. And so the current division principle is that this current I1 is proportional to Z2 over Z1 plus Z2. And current I2 is proportional to Z1 over Z1 plus Z2. Okay, so let's try to do something. We're going to skip this example because we're going to do one just like it. Okay, so we are asked to define the input impedance of this circuit given omega is equal to 10. So I'm going to break this up into three impedances. This is going to be Z1. This is going to be Z2. And this is going to be Z3. So who can help me derive an expression for Z1? So remember that this is 1 over J omega C. So Z1, yeah, go ahead.
For Z1, it would be 20 plus 1 over 20.
Yeah, it would be 1 over,
Oh,
yeah.
20 times 10 to the negative 3.
Yeah, so it's going to be like, sorry, I wrote 10. Just 10 times 0.002. So that's going to be equal to 20. I believe it's going to be minus J times 50, I believe. Right. Oops, terrible zero there. So this is 10 times 0.002 is equal to J is equal to 0.02, and 1 over 0.02 is 50. So if you have 1 over J times 50, oh, that's not right. Oh no, sorry. Now 1 over J50. 1 over J times 0.02 is equal to, and you move the J up top with a minus sign. And then the 1 over 0.02 is 50. What about the value of Z2? So I'm starting off, it's going to be equal to J omega times L. Oh, no, 1 over J omega over C. My bad. And this is the value of C we're going for.
Would it be negative J 25?
That sounds correct. Let's just verify. It would be right, 4 times 10 to the minus 3. So yeah, it'll be 4 over 100. So 1 over 25. So yeah, that's exactly right. Minus J25. And then Z3 is going to be equal to 50. That's the real component. Plus J, I'm just going to do this one. It's going to be 10 times 2, so J20. So now the question is, I have Z1, Z2, and Z3, and I want to know this. I want to know what I have to do with those three to get an expression for Z in. So what's the relationship between Z in and Z1, 2, and 3?
Z in would be Z1 plus the parallel of Z2 and Z3.
Exactly. That's excellent. That too. And then what I'm going to do for this point is just clear all this, and I'm going to show this written out. So Z1, Z2, and Z3. And so what I have to do here is this is Z1. And then I have to combine Z2 and Z3. They're in parallel. So you take their product and divide by the sum. Okay, so, and I'm sparing you of the complex arithmetic here, but basically what I did to go from this step to this step is that I multiplied this in Cartesian, I think, or yeah, however I did it. And I ended up with two complex number on top and a complex number on the bottom. And then to divide them, you can change in the polar form, do the division, change them back into Cartesian, and then perform the addition over here. Okay, so I think we have one more example to go through. It's this one, the last slide. And I like this one. So we are asked to calculate V naught. Okay. And so, first of all, what's in this circuit? We have a battery, which is sinusoidal. And then we have a parallel combination of a resistor and an inductor. And that parallel combination is then in series with a capacitor. So the first thing I'm going to get you guys to help me with is to express the battery as a phasor, the resistor, inductor, and the capacitor as a phasor. So first of all, let's represent the battery, which we're going to call, oh, not Z, VS. 10 angle 75. Excellent. That's exactly right. Oops. Let me go. 10 angle 75 is correct. And then what is the phasor corresponding to what is the impedance of the capacitor, sorry, of the inductor equal to? I'm going to call it ZL. Right, remember our omega is 10, right? J times 10 times 0.5, yeah, exactly. J times 10, so that's going to be equal to J times 2, or J times 5 rather. Yeah, 5J is right. I can't have the chat window open at the same time as the annotation. Super annoying. Okay, J times 5, and then the impedance of the resistor is just Z equals 10. And what about the impedance of the capacitor?
Is it 2J?
Yeah, minus 2J, I think.
Minus 2J.
Yeah, that's exactly right. So it's going to be, so it's 1 over J times 10 times 1 over 20. So we have J times a half at the bottom. So we have minus J2. And then we have, so what's the relationship here between, so how do I get V naught in terms of VS? what do I have to put in over here next to VS? What technique, what's the easiest technique that I can use to solve for V naught?
You would use current division.
But yeah, close.
I'm a voltage. Sorry.
Yeah. Voltage division is correct. Yeah, that's right. It was also correctly stated on the chat. So what's going to be my numerator and what's going to be my denominator? Right. This is the impedance of the voltage that you're interested in. So this is going to be negative J2. And the bottom is going to be negative J2 plus what? What's the impedance of this whole thing put together? Remember product over sum. So if I have Z in parallel with ZL, right, that just becomes product is 10 times J5. And the sum is 10 plus J5. So that becomes 50J over 10 plus J5, and there you'll have to, so I'm just gonna write this as 10 in parallel with J5. So now I have one complex number, which is here, multiplied by another complex number, which is here. I'm just going to switch back now to my, right, so we know this is the original expression where Z2 is just the impedance of the capacitor, and Z1 is the combination of the inductor and the resistor. And so it works out, we get nice easy numbers for these two combined, simplifies to 2 plus J4. And the way you get this, so this is going to become 550J, I believe. And this is 10 plus 5J. And so here's where you'll do that trick where you multiply the top and the bottom by the complex conjugate. And when you do that, you will end up with 2 plus J4. And Z2, which is the impedance of the capacitor, is minus J2. And so our source voltage is 10 angle 75. So then you just plug in all the numbers into the voltage division equation. And then you get a phasor multiplied by a ratio of complex numbers. And so negative J2 over 2 plus J2 is 1 over root 2 with an angle of minus 135 degrees. And then you do your complex multiplication. And if you want, I guess if you're asked, you transform your phasor answer back into the time domain. Okay, it's exactly 3:15 on my watch. So this is a good time for me to hand it over to the TAs. I'm gonna make Sam the host.
Thank you.
You're most welcome. I hope that you guys learned a lot in Flab, and I will see everybody back on a Wednesday.
Share. Okay, I think you can see my lab manual, right? There's no the green border on my screen, so I'm not sure if you can see it, but yeah.
Yeah, we can see it.
Okay, thank you very much. So just so you know, this it will be your session for next week. You will have to build this. Did you have a chance to look at the manual session, the module for this week? One moment. Let me open that to see. I don't know where to see the chat. Yeah. Okay, just so you know, today we will go through operational amplifier, and we will build 3 circuits. The first one is in like the inverting amplifier. The second one will be the non-inverting amplifier. And the third one will be, I think, the different amplifier. So for all of them, you will use the TL071CP op amp in your from your circuit kit. So I will show you in 1 second. I will stop sharing my screen and I will start my video. 1 second. Let me pull that thing out first. So just if you don't know what it look like, this is how it look like. There's the 8-pin of palm, and don't mistaken it with the other one, because this one only had a single dot on it on top of it, instead of like a dot and a things like, I think, do I have my picture? I don't have my picture. Shh, this is bad. Yeah, hang on. Where is my PDF? This is my PDF, and this is not what I think. I have to open it with this guy. Okay, this is much better. Boom, boom, boom. I think, yeah. Like, pay attention. I think there is only let me share my screen. And there's only for the TL, like if you can read it, there's only a single dot on one of the corner of your palm, instead of it look like this. If it's look like this is not the one. It's like there's only a single dot, and you will use it to identify the correct orientation for the up palm. So to go to quickly go over the up palm, so like you will use the single dot on top of like on the corner to correctly orientate your your palm in the breadboard. And for our purposes, we will like ignore the balance, the first pin. And then like if you learn in class, like even though like I think in one of the homework we did that, like we have like in the idea of palm, the powering voltage source have like is infinitely high, but in reality the V plus and V minus, there's a limit to them. And like in like for this lab session, we will connect the V plus and V minus to the 12-volt session in your circuit board in your and then I think correctly we will ignore the no connection as well. And like this one will be the like this one correctly show it over here. The number 2 will be the inverting terminal, and number 3 will be the non-inverting terminal. And the number 6 will be output, we can slightly ignore the balance pin as well. So for our purposes, we will concern only about this guy. Blah, 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 blah. So like for the inverting amplifier, I had my circuit built-in over here, and I will go through with you how I build this one. And your job is to replace the resistor with like I think the again the like we will have the R1 value over here fixed. And we will vary the RF value for all our inverting and non-inverting amplifier. So I don't remember what I set the fixed value was. I think I set it to 10K. Okay. Okay, so let's go over the circuit like image I have over here. Let me know if you have it. Just feel free to interrupt me if you have any question. Okay, so like I think we'll use this circuit as the, hang on, let me make it bigger. We will use this one as the basis for our circuit on the breadboard, and like if you read the lab manual, this guy will be 10K ohm, and this one will be vary for this for the purpose in the like for the resistor in the image. I think if I remember correctly, is 4.7K ohms, and so we know that this one is this one is the inverting terminal. So from this image over here, the both of like the inverting terminal will share a same node with both the R1 and the RF. So this is the inverting terminal, and so like this one will be number 2 over here. And then we have the number 3, which is the non-inverting terminal, convert to ground. So this one is ground, and this one is the output, and this one is ground as well. So we label it like this over here, GND. And this one is the output. So this one is number 6. And then we will also power this op-amp. So this one will be plus 12 volt, and this one will be minus 12 volt. And we have the voltage source coming in. So let's do it. Let me see. Ground and then inverting. Okay. And let me make my width a little bit smaller. Okay, I hope this works. Yeah. So this is the inverting terminal. So this one is pin number 1, 2, 3, 4, 5, 6, 7, and 8. And as we agree, the both the 10K resistor, this one is 10K resistor, 10K ohm resistor, and this one is 4.7K ohm resistor, and they are all share the same node. They both share the same node with the inverting terminal. So like we will connect them just like this, really simple. And then over here, I think it's the non-inverting terminal, and this one connect to ground. So I connect them from here to here, and just for reference, this one connect to ground over here. Yeah, this terminal is the ground. The green terminal is ground, and this one is on over here is the input voltage source, which I think we will use the wave generator to generate. I don't remember correctly. I think we will vary it from 1 volt to 5 volt. And it's quietly so yeah, so this one will, like the whole line over here will be connected to the ground terminal of the wave generator, in case you cannot see it. And then this one will be connected to the positive side of it. So we know this one is ground, and this one from the okay. So this one is 10K, and it's connect the voltage source to the 10K. We have the voltage source from the voltage source, the positive side to the 10K ohm. So we connect it just like this. It's really simple from here to here. And then like from here to here, we connect it to the 4.7K ohm resistor over here. And it will connect to the output. So we have the output, which is pin number 7 over here. And like for the clarifying purposes, I didn't use the jumper wire to bridge the 2 point over here, but you can always do that. This one, we just like, I will show you the path. So like for this one is the pin, it's come all the way to here, and then we connect from here to here. So this one make one single node, and this one is the output. And then I think we have this one, which is the V plug terminal, which will be used to power the up arm from here to here and from here to here. This one is I just make it for the beautiful purposes, for very easy to follow. So we connect it to from here to here, from here to here, and this one connect to either the V plus equal 12 volt, and like this one over here, like a little bit hard to see. No, right over here, terminal number 6. Connect to the V, I think is V minus. I going back on my work over here, but like this one is a negative terminal, which is equal to minus 12 volt. The both the 2 pin over here connect like this. And that's it. And to measure the output voltage, we will connect one probe of the oscillator into the output pin, which is over here at terminal number 7, which is share the same node with the 4.7K ohm resistor. And the other pin of the probe, which is like the ground probe, will connect also to the ground terminal, which is like on this line, on the blue line like this. And together we have a working circuit for the inverting terminal. I mean for an inverting op amp. And next step is we will do a wave generator. And to do this, I will need to connect this thing to my computer. Second. It's not powering up. Oh, maybe this guy. And I think for our purposes and make our life much easier, we will use the DC circuits over here, and the offset, like for this time, I'm not sure I include this thing in the, I think I include that one. We will set the offset to 1 volt. 1 volt should be enough. Let me do my calculation. Yeah, like let's do it 5 volt. And yeah, it's 5 volt, and run it. And then we have a scope, and we will run it as well. And yeah, this is, so if you do the calculation, if like the ratio between the RF and R1 is 4.7 R10, which is 0.7 0.47, and the DC offset we put into the circuits is 5 volt. And because this is an inverting amplifier, like so the absolute value of the voltage is 2.35 volt. And because this is an inverting amplifier, so the value will be minus 2.35 volt, which is exactly what we got over here. And let's yeah, the math check out. So I hope you like, I went a little bit too fast for the for the inverting amplifier. But if you can get it to work, then like you would just have to apply similar logic to build the non-inverting amplifier as well as the different amplifier. And that's it for my presentation. And now for the next part of our session, you guys will try it and let me know if you run into any problem. Any question? Hello.
Yes, Sam, I have a lot of questions. Can you bring the picture back again?
Which picture? Okay.
The one of the yes, this one. So can you just explain first where did you put in the voltages, and then like where is the ground and where is the 5 input and where is the scope input?
Oh, okay. So for this, for this purposes, what we are we are not like directly set the input voltage to 5 volt. We connect the power supply, like the power supply of the input voltage source of the op-amp into the wave generator over here. So like the terminal, whatever you decide to be the positive terminal of the voltage source will be like over here. And the ground, this time we will use the one that comes with the wave generator. So like for this, by doing this, we can vary the input voltage source using DC offset from 1 to 5 volt, and you will need that for your lab report. And then like your second question is like this one is used to purely power the op-amp over here. If you look at like I think the wire cover this, but this one is 12 volt and minus 12 volt. And you can like I use like these two row to like as the wire to power the op-amp. So this one is the negative terminal of the op-amp, and this will connect to this line. And this one is the positive, and it's a little bit difficult to see, but like it's connect from the terminal number 6 to this guy. And these two, we will give the op-amp 12 volt, and from the peak to peak will be 12 volt to minus 12 volt. And I think your last question would be the oscilloscope. The oscilloscope, we'll connect the oscilloscope. If you look at the image over here, this is the output, and the pin output on the op-amp is pin number 6. And the other side of the oscilloscope, to connect, to complete the circuit, we need to ground it. And to ground, we just need to connect the other side of the the other prop of the oscilloscope with the ground. So that's why what you are seeing here is one wire, the positive wire of the oscilloscope come into the output terminal of the op-amp. The second one will connect to the ground along with the ground from the wave generator. Did I answer your question?
Yeah, and how did you connect the resistors also?
Pardon me?
How did you connect the resistors?
Oh, like the resistor, if you look at like everything will be based on this image over here. So how do I connect the resistor? So for the 10K resistor, it will connect directly to the positive terminal of the voltage source. So what I did exactly, I did exactly that. I connect the one side, one terminal, one side of the resistor with the positive side of the voltage source. And then based on this image, the other side of the 10K resistor will share a same node with the inverting terminal of the op-amp, and one side of the RF resistor. So like all we have to do is to make sure all of these guys share a same node. And also I did exactly that, which is like we have this guy over here. Yeah, a little bit hard to see. I'll modify this number 1, number 2. And so this is the inverting terminal. So this one is the minus sign on your up arm. And you will connect it. This one, the entire line is one single node. So we can connect one terminal of the resistor with this into this column over here, and another leg of the resistor of the 10K resistor into this line. So together, this one is one single node, and we achieve that exactly as we planned. And then for the RF terminal, for the RF, what we can see is it connects to the output, like the other side, the other leg of the resistor connect with the output, and they share the same scope like terminal with the oscilloscope. So this is the other side. This is the other leg of the RF resistor. And like I use this wire to organize it. So basically it's go from here to here to here, which is the output terminal. This one is the output. And we connect it to, we connect it with with one probe of the resistor to measure the voltage.
Sam,
Thank you.
Yeah.
a quick question. The way that you numbered your op amp is different from how it shows in the lab manual.
No, if Tariq and I didn't make any mistake, then you should have 2 op amp which have a little, it will be a little bit hard to see, but it is TL. I think it's better to show it over here. This will be TL071CB, and it is the one has a leg and only a single dot on the op amp.
No, yeah, I got that. But what I'm saying is, like, if you scroll down a little bit, there, so go up where it numbers the pins for the op amp. You're the way you numbered them, 1, 2, like all those numbers for each pin is different on this op amp, this sample op amp versus the one that you numbered right now in the circuit.
Nope, it's not. Like what we are doing is like we use this dot over here to orient our op amp correct, like in the same orientation. So what I'm trying to do is I will show you. So this one has a leg. You know, like you can see, you agree, right? 1, 2, 3, 4.
Yes.
5, 6, 7, 8. And like it's a little bit hard to see, but there's a dot over here. And I will show you. And if like this is exactly the op amp on the circuit. This one, based on this position, this one will be number 1, number 2, number 3, number 4. Oh, I name it in the other, like in the other way around. Sorry. Yeah, number 8. Like this is A7.
Yeah, that's what I was trying to get.
Oh, okay. Sorry, my bad.
Okay, yeah. So
yeah, but like that's the idea. I'm really bad at remembering numbers like this. Yeah, sorry.
it's good. I just had a quick question. When you're connecting terminal 7,
Terminal 7. Yeah, this guy.
because that's the positive terminal, is that going directly into the positive 12 volts or is it the negative?
Yes. That will go directly into the 12 volt. And the terminal number 4 will go directly into the negative terminal of the thing. So number 4 over here. Yeah, we go like all the way in to the negative side. Can you see it?
Yeah.
We'll change this number.
Okay, I got it now. Thank you.
5, 6, 7, and 8. Okay, it's looking back. Okay, any more question? If not, you are more than welcome to try it. I think I will have to leave a little bit early, around 4:15, 4:30 today, because I have my vaccine appointment as 6, so I will need to leave a little bit early. Sorry about that. So try it and let me know if you have any question.
Sam, I'm
Yeah.
sorry. Can you show what we have to do on wave gen?
Hmm?
Can you show what we have to do on the application?
The application. What do you mean by that? Sorry about that.
On the waveforms?
On the waveform. So like this one waveform is really simple. All you have to do is I think for the assignment, you will have to, I think for experiment 1 and 2, you will have to vary it from 1 to 5 volt. The offset which are equivalent to 1, 2, 3, 4, 5 volt voltage supply to the op-amp, and you select the minus like the DC circuit, which is DC circuit, and then like just click run on the on the oscilloscope to obtain the value.
Sam, we don't have to make it look pretty like yours, right? So like we don't have to use all those jumper cables. We can just make one.
Nope, as long as it's work and I can say that like you are like connect the circuit correctly, that's fair for me. And then to make it look pretty, so like I can put it in the lab menu and you guys can follow it. But yeah.
Sam, just want to ask a question. What happens if we connected something wrong?
That's a really good question. I would say nothing. Like those op-amp has really good internal resistance. So unless you connect it directly to a DC with a really high frequency things, then it will burn it. But otherwise, it would be fine. Don't worry.
If it's burned, it's useless. Did you send another component of the same code?
Yeah, like I think in your circuit kit there two of the same component.
We have 2 of these op-amp.
Yeah, we're planning for
Okay.
you to do a different amplifier and a summation, but like since it would be too close to the final, so I think I will spare you guys with that. And just so you know,
Thank you.
one of the long thing, like I think I will include this in the lab manual, but you don't have to like do this for the final. I just want to let you know that's this small guy with I think 12 pin, 1, 2, 3, 4, 5, 6, 7, 14 pin. It contains 3 smaller op-amp with the same type that you got in like that you are working with. So like in a very bad case that you burn this one, you burn the smaller one, this guy can work for you as well.
Thank you. just wanna.
Sam, do you want us to include pictures for our op amps? I mean, our circuits?
Pardon me. Do you want like do I want you guys to take picture?
Yeah, to include in the.
Oh yeah. I think I will include that require. I will add that requirement into the lab report like later today.
And you want that for all of them, correct? Like all the modules?
Yeah.
Okay.
Yeah, I think I forgot to add that for the previous module. I will have to add that later today. But yeah, like you don't have to include all the pictures. Like for each experiment, like we vary the resistor. For example, from the previous one, we vary the resistor. You don't have to show me like all the image from for all the resistor. You just have to select one and show me, because like all the following, like for the same experiment, you just have to swap out a resistor. So if you got one correct, the other one should be automatically correct as well. The same thing for the op-amp amplifier. Like for each experiment, there's only one setup, and like to complete the lab report, you just have to swap out a component. So if you got the first one correct, then like I'm pretty sure you got the other one correct as well. Yeah, so
Okay.
yeah, it's a little bit complicated, but like once you get a hang of it, it's pretty fun. For next week, you guys have two options. Either I will like add one additional exercise experiment for this op-amp module, or I will reserve the session for question. So yeah, it's it's up to you guys. I think I will put out a poll on Slack somewhere. Just let me know.
So this is our last task.
Last module, like I'm still thinking whether or not I should do the an additional experiment, just one experiment, just to make sure that you guys fully understand how to use the op-amp, and to prepare you guys for Dr. Para and Dr. Bixen class, because like if you don't know how to use op-amp, they will kill you and they will complain to like that the BME 205 didn't do a good job in preparing you guys for those classes. Hello, can you hear me? Yeah, I think.
Yes.
Okay.
Just a quick question. When we're looking at WaveGen, how do we zoom out so that we can see the full line? Because right now I can only see up to -3.
-3. One moment. You mean this picture? You mean this picture? You mean this picture, right? Yeah, this one is a little bit hard to see. I have no idea. Like I don't have any solution. I try to take
No, so when you're looking at the graph itself on WaveGen, like it's just zoomed in. So I can't see like yours is from like -2.5 to 2.5. How do you like zoom out a little bit?
You don't have to zoom out, just click into the data button to get the correct value.
Okay, got it. Thank you.
Yeah, like this way easier, but like the graph is for you to see the general behavior of it, and this help you graph it really quickly. But like I think we can use, like, because we're using DC voltage, we can like safely ignore what is showing over here and just like look at the CV data, like the scope data. I think there's one question in the chat about explaining the table. You mean this table? Okay, so like I will go over this table a little bit as well. So like because we have the R1 value fixed to be equal to, I think I will include, like make this a little bit tiny bit bigger. 1.7. R1 equal 10k ohm, I think. And this one RF value, the idea of this table is you will like swap the RF with a 2.2k ohm resistor, and you will calculate the gain of it like in the combination of RF and R1. R1 is fixed at 10k, and you will calculate the ideal gain first, and then you will use the DC offset to vary the voltage from 1 to 4 volt. So what I mean was that you go into wave change, and you will change the voltage offset to 1 volt first, and then 2 volt, and then 3 volt, and then yeah, just input the voltage over here, and then calculate the actual gain that you get from this system, V1, V2, V3, and yeah. So yeah, you will do the ideal gain, and you will calculate the actual gain, which is the ideal gain over the actual like the input voltage equal gain, and that's a sign. And then for this one, swap the IF value to like 6.8k, calculate again, repeat the steps again, calculate the voltage.
So if we have change the input voltage value in the offset from 1 to 4, right? How is supposed to know the output voltage, where the datas are? What are the values of output voltage in the waveform generator, where I can trace what value I got for output voltage?
Like you have to make sure that like when you change, like for example, like we are doing 3 volt, then you will do 3 volt, you run it, and then you will go to the scope to check for the value. And yeah, like this value will change, and then you will go to, for example, and then I will change this to 4 volt, and I think it will reflect over here, and yeah, the value will change. So that's the idea. So did I answer your question?
Yes, thank you.
And you will do repeat the step for like all the like different type of like different value of the RF resistor. And then answer your question. I make a boo-boo over here. I will fix this. And then do the same thing for the second experiment. And for the third experiment, you will have the freedom to choose R1, R2, R3, and R4. And the idea was like based on whatever you choose value over here, you will calculate like the difference between these two using the formula in the manual and calculate it, and to calculate your ideal output voltage, and then using the oscilloscope to measure the actual value and to see if you can get it to be correct. And then next week we will work on this one. That's more fun. Like, yeah, we will build a GPU using a palm if you want to. Yeah, we will use this formula to calculate V0 and to get the difference between V1 and V2. I think we fix V1 at I think we fixed V2 at 5 volt. Now calculate V1. I think there's another chat question. Let me check. Okay. Stop sharing.
Sam, I have a question.
Go ahead.
For the oscilloscope, do we turn it on? Do we turn on the switch?
I think you should keep the switch at its original position, which is right over here. Hang on, I will share my screen. Like at right over here. Like if you switch into this position, you will need to use this one, and I don't know how to use it, so I advise you not.
Your screen is not shared, so I don't know.
Oh, okay, sorry, my bad. Yeah, so I think come on.
Because I remember in experiment 2, Tariq told us to switch it on.
We switch on. I think the only switch we're using is this guy. I don't think I ever tell you to touch this switch. Yeah, just keep this switch at this position and not this position, because otherwise you will have to use this guy. You're more than welcome to use it, but like it's a little bit annoying.
So the other guy is not. Okay, so the switch is not turning on and turning it off. It's basically just choosing which input we're using, right?
Yeah, like I think like you misunderstand. I think what I mean like in the previous experiment is we will use this oscilloscope over here as well as this guy, not like turning this guy up and down. Like we will use two of these to measure the voltage across two resistors simultaneously, and not like use only one and then like took off the probe, put it into another resistor. It took a little bit of time, but like it would work as well if you want to. But the idea is like we will use the jumper wire that come with the oscilloscope, connect it to the breadboard, measure the voltage across two pins. Did I answer your question?
Just 1 second. There's something here. My scope is yeah, it answered my question.
Okay, that's good to hear.
One thing is for this one, when I'm using the 4.7 and the 10 kilo ohm, I'm getting a V out of 3.6.
So you messed it up somewhere, I guess. 3 point. Like if your V in is 5 volt, then this should be 2 point something. Check the value of your resistor correctly. Maybe like you miscalculated some of the band, and like that's why like it result in a different value for the V output. I make some mistake, that's why.
Sam, for the scope, I'm not seeing any reading.
That's a really good side. Do you want to share your screen?
Yeah.
Okay, go ahead. Let me give you the permission to share. I think you have the permission.
I have a permission to share.
Okay.
So I turned on the 12. I connected the 12 to the positive and the negative.
Okay.
I connected the RF to the RF. I connected it to the negative.
Do you want
the output. So that's the scope that I'm having.
Đang ngầm học từ là blah 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 blah. Sorry, I was having some problem. Yeah, can you say that again?
Okay. So I connected the wavegun to ground and the positive of the input. I used the 10K resistor. Was it 10K? Yeah, I think it's the one that has orange in it.
Okay, yeah.
It's the brown, black, orange.
Yeah,
I connected to the positive, and I
okay.
connected to pin 2.
And
yeah, for pin 2, I also connected the other resistor with the other end to pin 6. And pin 6 is connected to the oscilloscope.
Okay.
And for pin 7, I connected to the positive.
Okay.
And for pin 4, I connected the negative 12 volts.
Okay, that's about right. And do you want to click on the data tab to see if we got the correct answer? Yeah, your value is about correct. I think the problem you are seeing is because your general offset is to the range of your division. Like if you want, like for the yellow box, change the range to like increase a little bit. The yellow
Increase
box.
it?
Yeah, to about 1 volt per division. Yeah, now you see it, you're like.
Okay. I see now.
Yeah.
5 volts, mate, because I'm using 5 volts.
Okay, yeah, after 5 volt, and then like you amplify it a little bit, yeah, and then you got about 10 volt, and it's not saturated because we're using 12 volt, so that's a good thing.
Okay, but I'm getting negative 10 though.
Yeah, because we are doing inverting amplifier. Come on, man.
Oh, so that's good.
Yeah, like we input the DC, like the positive value, like we get the negative value.
No, I mean it's different than the number you got. You got a different number though.
No, wait, what? Different value? I think I got a negative value as well.
Yeah, but you got like 2 point something.
Yeah, because maybe your IF value is different from mine. I use 4.7K. Maybe you use some different value for like you may use 47K.
I use 4.7.
4.7? I don't know. 5 times 4.7 divided by 10.
When I did 500 millivolts per division, it got me negative 2.7.
Oh, I know your problem. Okay, now you got 2.7. I think like when you use 5 volt and 10K and 4.7, I think you missed the position of the 10K and the 4.7. So if you do the calculation on my screen, I'm sorry about this.
You want me to stop sharing?
Yeah, so this is my calculation because like what I did was 4.7 out of 10K. That's why I got 2.37, 2.35. But if you got 10 of 4.7, you got 10.6, which is what you got, I think. And put the negative side because we're doing invert.
Also,
Inverting.
so I changed the.
Got it?
So I should change my my inputs, right?
Like you should swap the
Like
position. Like I think you should swap the position for the 10K and the 4.7K.
Although the picture is showing the same thing I did, which is weird. Okay, can I say that when I increased the range, when I decreased it to 500 millivolts per division, it decreased the number to negative 2.73185.
That is strange. Can you show me that? Can you share screens again? Thank you. That is really strange. Let me see. Let's see. Maybe it's saturated the range of the oscilloscope, I guess. That's my guess. And
So
yeah,
negative 2.7
yeah.
here.
So like technically
So
it's like saturated the range of your oscilloscope. So if you like make the value smaller, it will be even smaller. Wait, what?
so I should go big or should go small?
Like you should go bigger. Yeah. Yeah, now it's more correct. Like I think if you let the value too small, it will saturate the range of this oscilloscope and show its maximum value.
So it should. Okay,
like
let me swap them and see what happens.
Yeah, you can try that.
عايز ايه جوجو؟
I just saw your chart. I think what the output supposed to be is depend on your IF value and your DC offset value. I cannot answer that, but for our calculation, when IF equal 4.7K ohm for the inverting amplifier, 5 volt input voltage, the value is minus 2.37, 35 volt. You will have to do the math yourself.
So I'm still getting the same number.
That is strange. Do you want to show me your circuit? I can take a look.
Yeah, let me share the screen with my phone. Just 1 second. Uh, You can see my phone, right?
Yes. Oops. Okay. Let me see. Hang on.
Let me
Keep it
take a
steady.
picture so we can.
Yeah, keep it steady. I think I can take a screenshot and let me analyze it really quick. So yeah, I think
This
yes.
is the picture, so you can.
Okay, that's better. One moment.
If that angle is not working, you can tell me so I can change the angle.
I will take a look and let's see what we got over here. Screenshot and I will open this in PDF Expert. Yes. Okay, the 12 volt is correct. Yeah, you are like you need to swap the position of your 7. Like I will show you in your image. One moment.
Yeah, but that's how I had it the first time. So
Yeah,
let me swap it and.
yeah, and yeah, like this is what you had for the first time, I think. And let me check for your order like thing as well. So it's look correct, and yeah, everything look correct to me, and that's explain why you got 4.7 something, like 10 point something something, and like you can try
I'm
that.
confused, honestly.
Yeah, like if you swap it, it should give you the correct value. I don't know why it's not
But
good.
I swapped it though. I swapped it and I'm swapping it back again so I can share my screen one more time and give you a
Okay,
picture of how I had it the first time.
okay.
Let me
Like show me the way you think is correct, which is the 10K connect to the positive terminal, like to the voltage source, and the 4.7K connect to the output voltage.
so I'll show you. Just trying to get a good angle.
Yeah, what you are having problem is this guy and this guy over here. Come on, baby. Okay. Yeah, this guy and this guy over here. And beside that, everything look correct to me. Trouble.
Okay, can I share my screen now?
Okay. Go ahead.
Sam,
Go ahead.
question. The value you should be getting is 2.3, right?
Yeah, about that minus 2.3.
Yeah, minus. Okay, thank you.
Okay, does look good. Wow, we need to swap this. Okay, if you can rotate so I can take a picture, that would be really helpful. Thank you. Yes, that's
Yeah, I'm just.
yeah, I know it. I know it. Let me see. Okay, so everything look correct to me. So I don't know why you are getting still minus 10 point something. Let me check again. Yeah, everything. Oh, you are not convert, like you are not like connect the inverting terminal to the ground, or non-inverting terminal to the ground. Pin number 3.
Pin number 3.
Yeah, like you need to convert it to the ground.
Okay, thank you for noticing that.
Like if you look at my manual, there's a ground pin. Like this.
Yeah, the one that's coming from the generator, right?
Yes. The
Now how do we?
yeah, this
Yeah, now I'm getting negative 2.3.
Yay! Congratulations.
Thank you.
Yep.
Thank you, Sam.
Okay. Anybody else having problem? Some people quit already. Hope you are not coming back and ask me more questions. I think I will stop the lecture at 4:20 or 4:25 if you guys are good with that. If you have any more questions, feel free to send me a request for a Zoom meeting or send me whatever you got, and we can work together on that. And if too many people have the same problem, I think I will hold another Zoom meeting so we can meet. Like I can like address the problem together with you guys, just like we did this morning. Thank you very much. Okay, everybody is leaving. I think everybody should be good now. And I will got my second vaccine shot, and I hope I'm not out commission tomorrow. Bye bye. I will end our meeting now.